close your eyes gently. Take a deep breath. Let's travel together to the planet closest to the sun, a world of brutal extremes where day and night are implacable enemies, where time flows in ways that defy our intuition. Closer to the sun than any other planet in our system, Mercury orbits in that fiery region of space where sunlight is 7 times more intense than the light that bathes Earth. You might imagine this to be the hottest place in the solar system, a scorching inferno where nothing could exist without instantly melting. But the reality is more complex, more surprising. Mercury, despite its proximity to that nuclear furnace that is the sun, is not the hottest planet. That distinction belongs to Venus, that world covered in dense clouds, more distant but paradoxically more scorching. The reason for this apparent reversal lies in absence. Mercury does not have a dense atmosphere to trap heat, to create a greenhouse effect that maintains high temperatures. What little atmosphere exists is so tenuous, so rarefied, that it hardly deserves the name. A few atoms of sodium, potassium, oxygen, all stripped from the surface by relentless solar radiation or carried by the solar wind. It is almost a vacuum, offering zero protection, zero thermal insulation. And it is this absence of atmosphere that creates something truly extraordinary. Mercury exhibits the greatest temperature contrast of any world in our solar system. Think of the magnitude of this variation. During a Mercurian day, when the sun is high in the dark sky, surface temperatures can reach 430 degrees Celsius. That's enough heat to melt lead, to vaporize water instantly. The rock itself would glow faintly red if you could see it without being obscured by the sun's glare. But then, when night finally arrives, and it will eventually, though it takes an eternity, those same rocks that were melting during the day can cool to as low as 180 degrees Celsius below zero. That's cold enough to freeze solid carbon dioxide, to turn any water into rock ice. The transition between these extreme temperatures happens over Earth days, a slow but relentless shift from a scorching inferno to a deep freezer and back again. And about that day and that night, they operate on timescales that defy our everyday experience. A single day on Mercury, measured from sunrise to the next sunrise, lasts almost 59 Earth days. Imagine waking up on a Mercurian morning and knowing that the sun will remain in the sky for almost 2 Earth months before finally setting. And then the night would last another 2 months before the next dawn. It's an existence of eternal twilights, where time seems to have lost all familiar meaning. But here's the fascinating paradox. While a Mercurian day stretches for almost 60 Earth days, an entire year on Mercury, a complete orbit around the Sun, lasts only 88 Earth days. Mercury completes its journey around the Sun in less time than it takes to rotate twice on its own axis. It's a peculiar orbital dance, unique in the solar system, and this strange combination of slow rotation and fast orbit creates something truly bizarre. At certain specific points on Mercury's surface, due to the way the rotation and orbit synchronize, a single solar day, from sunrise to sunset, can last 2 entire Mercurian years. Think about it. You would see the sun rise, watch Mercury orbit the sun twice completely, and only then would the sun set. It's a temporal distortion that seems impossible, but it's simply the result of the unusual orbital mathematics of this near-sun world. Mercury spins on its axis with painful slowness, taking almost 60 Earth days for a complete rotation. But at the same time, it races around the Sun with furious speed, completing an orbit in less than 3 Earth months. It is the fastest planet in the solar system in terms of orbital speed, about 48 kilometers per second, compared to Earth's 30 kilometers per second. It is this speed that gave it the name of the winged messenger of the Roman gods. And the orbit itself is peculiar. Among all the planets, Mercury has the most elliptical orbit, the most elongated, the furthest from a perfect circle. It's almost like a flattened egg, with the Sun not at the center, but displaced to one of the foci of this ellipse. This means that sometimes Mercury is relatively close to the Sun, and at other times in its orbit it is significantly farther away. This variation in distance affects its speed. When it is closer, it accelerates, obeying Kepler's laws of planetary motion. When it is farther away, it decelerates slightly, and this elliptical orbit, combined with that strange rotation, creates visual phenomena that would be absolutely baffling to any observer on the surface. In some regions, during certain parts of the orbit, the Sun would appear to stop in the sky. Not moving forward, not moving backward, just suspended. And then, after remaining static for Earth days, it would begin to move again, but in the opposite direction, reversing across the sky before stopping again and resuming its original motion. It would be like watching time itself hesitate, reverse, and then continue. The culprit behind many of these peculiarities is the solar tidal force. Mercury is so close to the Sun that solar gravity doesn't pull uniformly across the planet. It pulls more strongly on the near side than on the far side. Over millions of years, this subtle but persistent difference has warped Mercury's rotation, locking it into a peculiar resonance with its orbit. It's as if the Sun has gravitationally grabbed Mercury and twisted its rotation until it found this strange but stable configuration. When we look at the surface of Mercury, we see a world that strongly resembles our own moon. It is covered in craters, thousands of them, some tiny, others gigantic, all silent witnesses to billions of years of bombardment by asteroids and comets. Without an atmosphere to burn up meteorites before they hit the ground, each approaching object impacts with full force, carving a new scar on the already marked surface. The largest of these scars is the Calorus Basin. Calorus, meaning heat in Latin, aptly named because it is located at one of Mercury's hot spots, where the Sun is most intense. This basin is 1,550 kilometers wide, large enough to swallow the whole of France. It was created by an impact of an asteroid or comet so massive, so violent, that it is difficult to comprehend the energy involved. And here's something extraordinary. The impact that created Calorus was so catastrophic that seismic waves traveled across the entire planet, converging at the exact opposite point. When these waves met on the opposite side of Mercury, the surface there was literally shattered, creating a chaotic terrain of hills and valleys. It's as if the entire planet rang like a giant bell, and the focal point of this resonance was permanently deformed. Mercury has mountains, but they didn't form the way terrestrial mountains do. There are no tectonic plates on Mercury, no active volcanism pushing material upward. Instead, these mountains, called lobed scarps, formed when the entire planet shrank. As Mercury cooled over billions of years, its interior contracted. The rigid crust on the surface had no choice but to bend and break, creating false steep cliffs that extend for hundreds of kilometers. And the planet has indeed shrunk measurably. Estimates suggest that Mercury has decreased by about 7 kilometers in diameter. Imagine an entire planet getting smaller, its surface being compressed, folded, fractured, while the interior cools and contracts. It's geology operating on a planetary scale, a slow squeezing that has continued for eons. The reason for this dramatic shrinkage lies hidden within the planet. Mercury possesses a disproportionately large iron core, occupying about 85% of its inner radius. It is the largest proportional core of any planet in the solar system. If you could cut Mercury in half, you would see a thin, rocky shell enclosing a huge sphere of partially molten iron. Why does Mercury have such a large core? Perhaps it was born that way, formed from particularly metal-rich material, or perhaps, at some distant point in its past, a gigantic impact ripped away much of its rocky mantle, leaving behind mostly the dense core. And this giant iron core is still partially molten, still in motion. And where there is liquid iron in motion, there is the possibility of a magnetic field. Mercury has one, although it is weak, about 1% of the strength of Earth's magnetic field. But even this weak field is enough to create a small magnetosphere, an invisible bubble that partially deflects the solar wind, protecting at least part of the surface from the most intense radiation. Interestingly, this magnetic field is not symmetrical. It is significantly stronger in the northern hemisphere than in the southern halves, as if the internal dynamo that generates it were off-center, tilted, operating in an unbalanced way. Scientists are still debating why this happens. Perhaps it is due to the peculiar shape of the core, or to the way liquid iron circulates deep inside. Breathe gently. Visualize Mercury slowly rotating under the intense glare of the sun. There is so much more to discover about this small world of extremes. Mercury's history may be one of catastrophic loss. Planetary scientists speculate that the small world we see today may have been, in a violent and distant past, a significantly larger planet. But then, in the chaotic early days of the solar system, when massive objects still wandered in unstable orbits, colliding and fragmenting, Mercury may have suffered gigantic impacts that literally ripped away much of its outer structure. Imagine the scale of this violence. Estimates suggest that up to 70% of Mercury's original material may have been ejected into space by these cataclysmic impacts. The rocky mantle, that thick layer of silicates that should have surrounded the metallic core, was partially shattered and dispersed. What remained was mainly the dense core of iron and nickel, surrounded only by a thin shell of surviving rock. That's why Mercury has one of the most extreme core-to-total size ratios in the entire solar system. That metallic core occupies approximately 85% of the planet's total radius. If you could visualize Mercury in cross-section, you would see an immense ball of iron with only a relatively thin, rocky covering, like a nut where the shell is surprisingly thin compared to the dense kernel. And this core, despite being ancient, still generates a magnetic field. It's true that it's weak, only about 1% of the strength of Earth's magnetic field. To put that into perspective, a compass would work on Mercury, but it would barely be able to move, trembling weakly toward the magnetic poles. But even this weak magnetosphere accomplishes something important. It partially deflects the solar wind, that constant stream of charged particles that the sun throws in all directions. Without this minimal, however tenuous protection, Mercury's surface would be even more severely damaged by solar radiation. But the magnetosphere creates a small protective bubble, a region where the solar wind is deflected at least partially, around the planet instead of hitting it head-on. And here's something truly surprising. Mercury has a tail, just like a comet. Not a tail of sublimating ice like we see in comets, but a tail of sodium atoms ripped from the surface by the relentless force of solar radiation. These sodium atoms glow when excited by sunlight, creating a faint but observable tail that stretches millions of kilometers into space, always pointing away from the sun, pushed by the solar wind like hair blown by a giant fan. Sodium comes directly from Mercury's rocky surface. Intense solar radiation, remember, 7 times stronger than on Earth, literally rips atoms from the rock, a process called sputtering. It's as if the sun is slowly vaporizing Mercury, atom by atom, in a process so slow that it will take trillions of years to have any measurable effect, but it is still happening, constantly, inexorably. The surface is, in a very real sense, evaporating. Not rapidly, not visibly, but over billions of years. Microscopic layers of material are being lost to space, contributing to that sodium tail, gradually changing the composition of the exposed surface. But here is one of the most surreal contrasts in the entire solar system. Mercury, that scorching world closest to the sun, possesses water ice. Not spread across the surface, of course. Any ice exposed to direct sunlight would sublimate instantly. But in deep craters near the poles, craters whose high, steep rims cast eternal shadows inside, sunlight never reaches the ground. These eternally shadowed craters are cold traps. Any water that somehow reaches them, perhaps delivered by impacting comets billions of years ago, is trapped, frozen, preserved in perpetual darkness. The temperature in these shadowed havens can drop to as low as 170 degrees Celsius, even on a planet with the most extreme daytime temperatures in the solar system. It's a frozen oasis in a scorching desert, a contrast that seems impossible but is perfectly real. When we compare Mercury to other bodies in the solar system, we discover something humbling. This entire planet, this world that orbits our star as one of the 8 main planets, could comfortably fit within the diameter of some gas giant moons. Ganymede, Jupiter's largest moon, is significantly larger than Mercury. Titan, that fascinating moon of Saturn with its dense atmosphere and methane seas, also surpasses Mercury in size. It's a reminder that planet is a designation of position and formation, not necessarily of size. Mercury is a planet because it formed through the direct collapse of material in the solar nebula, because it orbits the sun directly, because it has enough gravity to be spherical, and because it has cleared its orbit of other debris. But in terms of sheer size, some moons surpass it, and without a true atmosphere, only that extremely tenuous exosphere of transient atoms, Mercury is a world of absolute silence. Sound needs a medium to propagate. It needs air molecules colliding with each other, transferring vibrational energy. On Mercury, with its exosphere 1 trillion times more rarefied than Earth's atmosphere at sea level, there is not enough of a medium to carry sound. If you could stand on the surface, protected from the heat and radiation, and clap or shout, you wouldn't hear anything. No echo, no reverberation, just absolute silence. It's a silence deeper than any stillness you can experience on Earth. A silence that would be almost oppressive in its totality. Sunlight, however, would be anything but silent in its intensity. It is up to 10 times stronger on Mercury than on Earth. If terrestrial sunlight at midday can burn your unprotected skin in minutes, Mercurian sunlight would do it in seconds. It is radiation so intense that any spacecraft landing there needs massive heat shields, specialized reflective surfaces, and active cooling systems to avoid simply being baked. And when you look up at that brutally illuminated surface, you don't see a comforting blue sky. Mercury's sky is completely black, even at midday, even with the sun shining 10 times brighter than we see it from Earth. It's as black as night, sprinkled with stars visible even during daytime, with the sun appearing as a bright white disk 2.5 times larger than we see it from Earth. This happens because there is no atmosphere to scatter sunlight. On Earth, our sky is blue because air molecules preferentially scatter blue light, sending it in all directions and creating that familiar blue dome. But on Mercury, sunlight travels in a straight line from the sun to the surface and reflects back, without scattering. The sky remains black, the stars remain visible, and the contrast between sunlit surfaces and shadowed areas is absolutely brutal. No smooth gradations, just sharp boundaries between blinding light and profound darkness, and the surface itself continues to tell stories of contraction. Mercury has giant faults called rupes, scarps that extend for hundreds of kilometers, some reaching heights of 2 to 3 kilometers. These are not tectonic faults in the terrestrial sense, created by plates moving against each other. They are compression features, created when the entire crust was compressed as the planet shrank. It's like watching the skin of an apple wrinkle as the fruit dries and shrinks, but on a planetary scale. Mercury is slowly, inexorably shrinking, and these rupes are the visible marks of that process. The planet we see today is slightly smaller than the planet that existed billions of years ago, and it will continue to shrink, imperceptibly but persistently, as its interior continues to cool and contract. Mercury's scarps deserve deeper contemplation. These gigantic faults, these scars on the landscape, can stretch for thousands of kilometers, distances that encompass entire countries on Earth. Imagine standing at the base of one of these scarps, looking up, seeing a cliff that rises for kilometers and extends beyond the horizon in both directions. These are not features formed by colliding tectonic plates, but rather by the slow and inexorable contraction of an entire planet as its metallic interior cools and solidifies. These scarps are, in essence, planetary wrinkles, permanent marks of a world that is shrinking. Over billions of years, since Mercury formed as a swirling molten mass in the primordial solar nebula, its interior has gradually cooled, and as it cools, it contracts. The rigid crust on the surface has no choice but to crack, fold, and pile up upon itself, creating these massive faults. The total shrinkage since its formation could reach a reduction of 7 kilometers in diameter. Think of the scale of that. An entire planet, shrinking, becoming smaller, its surface being compressed like a drying apple. Its geology in super slow motion, but operating on a scale that defies comprehension. And Mercury's internal structure is unique among the rocky planets. It is the only one where the metallic core exists simultaneously in solid and liquid states. The inner core is solid, iron and nickel crystallized under immense pressure, but around it there is a layer of molten metal, still liquid, still in convective motion. It is this movement of conductive liquid metal that generates Mercury's weak but persistent magnetic field. And this core, in both states, occupies an absurd 85% of the planet's diameter. Mercury is, in essence, a giant ball of metal with a thin crust of rock. If you could weigh Mercury and compare its density to other rocky planets, you would find that it is disproportionately dense, heavy for its size. It is this extreme concentration of metal that makes it so. When we look at the surface of Mercury through telescopes or through the eyes of space probes, we see a landscape that powerfully resembles our own moon. Craters upon craters, impacts superimposed on previous impacts, layers of geological history written in circular scars. But some regions of Mercury are even older than the oldest regions of the Moon, preserved because there is no atmosphere to cause erosion, no water to wear away features, no winds to accumulate dust. And some of these craters possess an extraordinary characteristic. They are so deep, their rims so high, that the interior never receives direct sunlight. They are pits of perpetual darkness, shadow traps that have remained dark for billions of years. The sun spins across the black sky over endless Mercurian days, but these craters remain in eternal night, and in those permanent shadows, the temperature can plummet to 200 degrees Celsius below zero. That's colder than the night side of Mercury, colder than many regions of the outer solar system. It's a deep, impenetrable cold, preserved by the sheer absence of sunlight in a world where sunlight is usually overwhelmingly intense. And it was in these regions of perpetual shadow that the MESSENGER probe made a completely unexpected discovery: deposits of water ice. On Mercury, the closest planet to the Sun, where daytime temperatures can melt lead, ice exists. It's one of the most surreal contrasts in the solar system, a scorching inferno separated from a deep freezer by only a few kilometers, divided only by the presence or absence of direct sunlight. This ice likely arrived via cosmic deliveries over billions of years. Comets, those dirty balls of ice and rock that wander the solar system, occasionally collide with Mercury. Most of the water they bring vaporizes instantly on impact, but some molecules, by sheer luck, bounce into these shadowed craters before the sun can vaporize them. And there, in that icy darkness, they remain trapped indefinitely. When we observe Mercury from Earth, it appears surprisingly bright in the twilight sky, visible briefly after sunset or before sunrise, always near the horizon, always closely following the sun. You might imagine that this is because its surface is highly reflective. But the truth is the opposite. Mercury is dark, almost black, reflecting only about 12% of the light that hits it. It is as dark as coal, as fresh asphalt. What makes it visible and bright is simply its proximity to the sun. It is so intensely illuminated, even with its dark surface, that enough light is reflected to make it one of the brightest objects in our sky. It's a trick of geometry and luminous intensity, not of high albedo. And it is this extraordinary orbital speed, those 48 kilometers per second, that inspired its Roman name. Mercury, the messenger of the gods, the winged god who flew swiftly between heaven and earth, carrying messages. And from this celestial speed comes our term mercurial, used to describe something fast, volatile, difficult to fix or predict. It is appropriate for a planet that moves so quickly across the sky that ancient civilizations noticed it and distinguished it from the fixed stars. Mercury's orbital dance with its rotation creates a unique resonance in the solar system, a 3-to-2 ratio. For every 3 rotations Mercury completes on its own axis, it completes 2 orbits around the Sun. This synchronization, this specific ratio, is the result of billions of years of solar tidal forces gradually shaping the rotation until it settled into this stable configuration. And this resonance creates that temporal peculiarity we mentioned before. A complete solar day on Mercury, measured from noon to the next noon, lasts an incredible 176 Earth days. That's almost half an Earth year of uninterrupted sunlight, followed by another almost half a year of night. It's an existence of extreme seasons where morning and afternoon lose any familiar meaning. And let's return to that extraordinary visual phenomenon. In certain regions of Mercury, during certain parts of its orbit, an observer on the surface would see the sun do something impossible. Stop, literally pause in its movement across the sky, remain fixed for Earth days, and then begin to move in the opposite direction, reversing before stopping again, and finally resuming its original path. It's an illusion created by the combination of the elliptical orbit and rotational resonance, but it would be absolutely baffling to witness. Mercury's landscape has subtle features that are easily missed when focusing on the dramatic craters. There are gentle slopes, soft undulations that stretch for hundreds of kilometers, like frozen waves in an ocean of rock. These may have been created by ancient lava flows billions of years ago, when Mercury was still geologically active, when its interior was hot enough to melt rock and send it flowing through fissures to the surface, and humanity has left its mark on Mercury's craters, not physically, but nominally. Following a tradition established by the International Astronomical Union, craters on Mercury are named after artists, musicians, and writers who have made significant contributions to human culture. There is a Beethoven crater, marking the surface with the name of that deaf composer who created symphonies he could never fully hear. There is a Rembrandt crater honoring the Dutch painter, a master of light and shadow, appropriate for a world of such extreme contrasts between brutal sunlight and absolute shadows. Although Mercury has no true atmosphere, it does have that extremely tenuous exosphere we mentioned. It is composed of atoms released from the surface, primarily sodium and potassium, but also oxygen in minuscule quantities. These atoms are ripped from the rock by the solar wind, intense radiation, and micro-impacts from interplanetary dust. They bounce around the surface in ballistic arcs, eventually escaping into space or being replaced by new atoms ripped from the rock. And the solar wind, that constant stream of charged particles from the sun, not only rips atoms from the surface but pushes them away, creating that sodium tail we described earlier. It's invisible to normal visible light, but it shines at specific wavelengths when observed with appropriate instruments. Mercury travels through the inner solar system with this ethereal tail following behind, like a ghostly cloak blown by stellar winds. Take a deep breath. Visualize those eternally shadowed craters hiding ice. That sun standing still in the sky before setting. There are even more wonders in this little messenger of the gods. These lobed scarps that crisscross Mercury's surface are geological monuments to planetary contraction. Gigantic cliffs stretching for hundreds of kilometers, some reaching heights of 2 or 3 kilometers, equivalent to terrestrial mountain ranges, but created by a completely different process. They are not the result of colliding tectonic plates, but rather permanent marks of a planet that literally shrank, its surface being compressed, folded, and piled upon itself as the interior cooled. And the magnitude of this shrinkage is impressive when you really contemplate it. Mercury has shrunk by approximately 7 kilometers in total radius since its formation. This means that the planet's diameter is now 14 kilometers smaller than it was billions of years ago. It's as if the entire planet has been placed in a gigantic press and gently but inexorably compressed over eons. This shrinkage caused colossal cracks in the crust, faults where entire sections of the surface were pushed over adjacent sections, creating those dramatic cliffs. And Mercury is unique among the rocky planets for exhibiting this shrinkage so clearly and extensively. Mars, Venus, Earth all have tectonic features, but none show this global pattern of contraction in the same way as Mercury. And let's return to that extraordinary core. More than 80% of Mercury's total diameter is occupied by this dense metallic core. To put that into perspective, if Earth had the same proportions, our core would extend almost to the surface, leaving only a thin shell of mantle and crust. Mercury is, in essence, a metallic planet disguised as a rocky planet. A giant ball of iron and nickel with only a relatively thin covering of silicates. And this disproportionately large core is one of the great unsolved mysteries of planetary science. Why does Mercury have so much metal? Why is its core-to-mantle ratio so radically different from all other rocky planets? Scientists debate various theories, each attempting to explain this peculiarity. A dramatic theory suggests an ancient catastrophe. Perhaps in the chaotic early days of the solar system, when orbits were still stabilizing and collisions were common, Mercury was struck by a Mars-sized protoplanet. The impact would have been cataclysmic, vaporizing and ejecting much of Mercury's rocky mantle into space, but leaving the dense core intact. What we see today would be the surviving core, enveloped only by the remnants of the original mantle. Another theory, less violent but equally intriguing, points to its formation. Mercury condensed so close to the Sun, in such a hot region of the primordial solar nebula, that only the densest materials with the highest melting points managed to solidify there. Lighter materials, less dense silicates, remained vaporized or were blown to more distant regions by the pressure of solar radiation. Mercury would therefore have been, from birth, a world enriched in metal. And this giant core, although partially solidified, still generates a magnetic field. It's true that it's weak, about 1% of the strength of Earth's magnetic field, but it's enough to create fascinating phenomena. Mercury has auroras, although they are profoundly different from the dazzling displays of green and red light that dance in Earth's polar skies. Mercury's auroras are not colorful. There is no thick atmosphere for energetic particles to collide with, exciting atoms that then emit visible light. Instead, they are simply emissions of energetic particles, X-rays and ultraviolet, invisible to the human eye, but detectable by instruments. And, curiously, they occur on the day side of the planet, not on the night side like on Earth, because that is where the solar wind impacts the weak magnetosphere more directly. The interaction between the solar wind and Mercury's surface creates peculiar magnetic structures called magnetic swirls. These are regions where the magnetic field twists into complex patterns, allowing the solar wind to penetrate deeper and interact directly with the ground. These regions develop distinctive visual features, areas of extremely bright ground called swirls, swirling patterns visible in high-resolution images, as if someone had painted swirls on the surface with light-colored paint. And Mercury is constantly bombarded. With no atmosphere to burn up meteoroids before they hit the ground, every bit of space dust, every tiny rocky fragment that crosses Mercury's orbit impacts with full force. Thousands of micrometeorites hit the surface every day, each minuscule impact creating a small crater, vaporizing a tiny amount of rock. And each of these impacts, however small, releases metallic vapors, atoms of sodium, potassium, calcium, all ripped from the rock by the shock of the impact, hurled into the tenuous exosphere. It's a continuous process of impact erosion, slowly sculpting the surface atom by atom over billions of years, constantly contributing to that ghostly atmosphere that envelops the planet. And that exosphere is so incredibly rarefied that individual particles can travel kilometers, tens of kilometers, before colliding with another particle. It's almost a perfect vacuum, with only fleeting traces of matter. A sodium atom ripped from the surface can bounce in a high ballistic arc, rising hundreds of kilometers above the surface before falling back down. And during that entire journey, it may not encounter any other atom. This exosphere is composed primarily of sodium, potassium, oxygen, and helium. When exposed to intense solar radiation, these atoms absorb specific photons and re-emit them, creating a faint but detectable luminescence. It's like a ghostly aura around the planet, invisible to the naked eye, but bright at specific wavelengths. And some of these atoms, particularly sodium, don't fall back down. Instead, they are caught by the solar wind and carried away, forming those atomic tails we mentioned. It's a trail of escaping sodium, forming a structure similar to a comet's tail. This bright tail extends for thousands, sometimes millions of kilometers into space, always pointing away from the sun, pushed by radiation pressure and the solar wind. And surprisingly, this tail can even be detected from Earth. Using telescopes equipped with special filters tuned to the spectral lines of sodium, astronomers can observe this faint but real structure. Mercury leaving a bright trail as it orbits, like a planetary version of a shooting star, but in cosmic super slow motion. It's a reminder that Mercury, despite being a solid rocky planet, is slowly evaporating. Not quickly, the process will take trillions of years to have any measurable effect on the planet. But it is happening, constantly. Atom by atom, Mercury is being scattered into space, its surface slowly carried away by the solar wind, creating that ethereal tail that accompanies it on its perpetual journey around the sun. Mercury's surface is a living archive of the solar system's ancient history. Some of the craters that mark its rocky face are over 3,800,000,000 years old, formed during that chaotic period known as the Late Heavy Bombardment, when asteroids and comets wandered in unstable orbits, frequently colliding with the inner planets. And many of these craters have never changed since their formation, without erosion by water, without alteration by the atmosphere, without tectonic plates recycling the crust. These features remain almost exactly as they were at the moment of impact. Mercury is, in essence, a fossil planet, preserving on its surface a record of our system's violent youth. In the distant past, when the sun was younger, more active, and more violent in its eruptions, Mercury was even more brutally punished by radiation. The young sun went through periods of extreme activity, gigantic solar flares, frequent coronal mass ejections, and solar winds far more intense than today. Mercury, in that exposed position so close to the stellar furnace, absorbed the worst of this fury. It's hard to imagine, but the already brutal environment that Mercury experiences today is actually calmer than the inferno it was billions of years ago. and with each slow rotation, Mercury experiences extreme thermal cycles. The planet loses heat rapidly during the night. Without an atmosphere to act as an insulating blanket, infrared radiation escapes freely into space. The temperature plummets from 400 degrees above zero to almost 200 degrees below zero in a matter of Earth hours, as the surface rotates from brutal sunlight to shadow. It's a relentless thermal seesaw that repeats itself every endless Mercurian day. And here's one of the most surreal contrasts we can imagine. Mercury is one of the very few places in the universe where you could theoretically find water ice and temperatures of 400 degrees Celsius on the same day, separated by only a few kilometers. The shadowed craters at the poles keep ice frozen at 200 degrees below zero, while nearby illuminated areas are hot enough to melt zinc. It's like having the Arctic and the Sahara occupying the same space, divided only by a line of shadow. Mercury is classified as geologically dead. There is no active volcanism, no moving tectonic plates, no significant earthquakes. But there are abundant signs of ancient activity. Billions of years ago, when its interior was still much hotter, gigantic lavas erupted through fractures in the crust. These lavas flowed in vast floods, filling ancient craters, creating smooth plains that contrast with the heavily cratered terrain around them. Some of these lava plains stretch for thousands of kilometers, frozen testimonies of an era when Mercury still had internal geological life. The contraction scars that crisscross the planet, those lobed scarps we've visited several times, can be described as wrinkled faults, as if the entire surface had been crumpled like paper. They stretch for thousands of kilometers, some of the longest and most continuous tectonic features on any rocky planet. If you could place these faults on Earth, they would cross entire countries, stretching from Spain to Russia, or from the east coast to the west coast of the United States. And let's recall the magnitude of that shrinkage. A 7-kilometer reduction in total diameter since its formation. That's extremely rare among planets. Earth didn't shrink like that. Mars didn't shrink like that. Venus certainly didn't. But Mercury, with its disproportionately large metallic core, experienced thermal contraction on a scale that left permanent, global marks on its surface. This shrinkage is a direct result of the cooling of that immense metallic core. As the iron and nickel inside cool, they contract. It's a fundamental property of matter. And because the core is so large, occupying 85% of the planet's interior, this contraction affects the entire planet. The crust on the surface is forced to adjust, to compress, creating those massive faults we see today. It has the most extreme core to total size ratio of any rocky planet in the solar system. Mercury is more metal than rock, more core than mantle. It is a planet that challenges our expectations of how rocky planets should be structured. Mercury's magnetic field is so weak that it went unnoticed for decades. It was only definitively detected when the Mariner 10 probe passed by the planet in 1974, its sensitive instruments finally capturing that faint field. And even now, with more precise measurements, it remains surprisingly weak, about 1% of the strength of Earth's field. A compass would work, but barely, trembling weakly, struggling to align itself. And this field is not symmetrical. It is significantly stronger in the northern hemisphere than in the southern, as if the internal dynamo that generates it were off-center, tilted within the planet. Perhaps the liquid core does not uniformly fill the available space. Perhaps the convection that generates the field is more active in one region than in another. It's yet another mystery on a planet full of them. Solar winds, that constant stream of charged particles from the sun, strike Mercury with force unchecked by a robust magnetosphere. These energetic particles literally sand the surface, stripping away atoms, slowly altering the chemical composition of the surface layers, darkening the rock over eons through a process called space weathering. And during solar storms, when the sun ejects enormous masses of plasma in violent eruptions, Mercury's tiny magnetosphere is drastically compressed. The intensified solar wind pushes against it, squeezing it, sometimes compressing it so much that solar plasma directly hits the surface in some regions. It's as if Mercury is periodically stripped of its already inadequate magnetic protection, becoming completely exposed to the stellar fury. Cometary structure of sodium atoms constantly being torn away and scattered. It is formed by solar radiation and the solar wind working together, vaporizing atoms from the surface and then pushing them away. This tale can be seen from Earth with appropriate equipment, filters tuned to the characteristic spectral lines of sodium, revealing a tenuous but real structure extending millions of kilometers into space. Despite being the innermost planet in the solar system, despite being intensely studied by terrestrial telescopes and visited by space probes, Mercury still holds many mysteries. Why is its core so disproportionately large? Exactly how and when did those lava plains form? Are there subtle geological processes still happening that we haven't detected? What is the exact composition of that ice in the polar craters? Is it pure water or mixed with other compounds? And there is hope for answers. The Bepi Colombo mission, a collaboration between the European and Japanese space agencies, is now on its way to Mercury. Launched in 2018, it uses a complex series of gravitational assists to gradually reduce its speed, preparing to enter orbit around Mercury. When it finally arrives and begins its detailed observations, it will reveal secrets that Mercury has kept for billions of years. Details about its composition, its internal structure, its geological history, perhaps even clues about how rocky planets form so close to their stars. Take one last deep breath. Let the images of Mercury float through your sleeping mind. That small world marked by extremes, slowly spinning under the relentless glare of the sun, its surface divided between scorching inferno and dark freezers, its ancient craters guarding impossible ice, its giant core generating weak magnetic fields, its ethereal tale of atoms escaping into the cosmos. Good night. Sleep well. Dream of rocky worlds spinning beneath blazing suns, where days last for months and ice survives alongside molten rocks.